Hi everyone, welcome back to Mind and Maths with Amna. In today's lesson, we are going to study how output adjusts over time when expectations are adaptive. People don't instantly change what they think about the future, they actually update slowly based on what actually happened in the past. This slow adjustment creates dynamics in income, consumption, and output. We'll derive the difference equation, find the general solution, and then clearly interpret the short run, medium run, and long run fiscal multipliers. So, by the end of this lesson, you'll see exactly how expectations shape the path of the economy, not just the final outcome. So, I've already written down how the expectations of output in period time t uh, uh, are described. It's basically a weighted average of the actual realized value of output in the previous period and what was expected in the previous period. So it's basically weighted average of what actually happened and what was expected to happen, where lambda is basically the speed of adjustment to new information. So, moving on, suppose we have this model. This is the goods market Keynesian cross model, where we have y is equals to c plus I plus g, and the expected value of output is given by the adaptive expectations model. So by this equation, suppose for simplicity, investment is autonomously set, and government spending is also autonomously set, and it is constant. But suppose that consumption at time t depends not on the realized value of output at time t, but what was expected. Okay, so first of all, let's put in the value of these functions into the main equation. So this is the value of c, and then we have I, and then we have a g. We can put all the constants together, and then we can put y e t plus ut on the right side. Okay, so the problem with this expression is that we have an expected value of yt, whereas in a difference equation I want basically yt in terms of its own lagged variable, which is realized. It's the actual value, not the expected value. So basically I need to get rid of this expression, and how can I get rid of it? I can get rid of it by using the equation that actually gave us how expectations were formed. So moving on, let's try to find out this expression. Okay, if I plug this expression into this equation, I'm still going to be left with an expected value of the previous period once again. So I need to keep substituting back. So for instance, when I substitute one more time, what am I going to get over here? I'm simply going to lag this equation by one time period. So I'm going to get a lambda yt minus 2 plus 1 minus lambda yt minus 2, which was expected. Okay, let's open this up. Lambda yt minus 1 plus lambda into 1 minus lambda yt minus 2 plus 1 minus lambda square y expected value at t minus 2. As you can see, once again we have an expected value here which we don't want. So let's just remove it one more time and we'll be able to see a pattern being formed. So let's lag which expression? This expression, because this was the expression for expected output at t minus 1. I'm going to lag it one period behind to get the equation for the expected value of output at t minus 2. So which is going to be lambda y t minus 3 plus 1 minus lambda expected level of output at t minus 3, and that's it. I think this much is enough because now we can see a pattern being made. So I'm just going to open this up, and I think most of you should be able to detect a pattern. Power 3 y e t minus. As you can see, the equation goes like this. If I do it, there's a lambda in all of these expressions, so I can do a lambda, I can take it out, and then I can make a summation sign, and I can say it is each expression is being multiplied by a 1 minus lambda. Then we have a y t minus something. So when this was to the power 1, I had a 2 here, and when it was at a power 2, I had a, oh, this was actually a 3, sorry. Then I had a 3 here. Yeah, my bad. Minus 3. So whatever the number is over here, the number that we have to subtract is just 1 higher. So if I have a I here, then I'm going to have a I plus 1 here. And this goes from I 0 till infinity. Okay, remember that there's no point in me mentioning the fact that the last term is not actually being multiplied by a lambda because I'm just taking this series till infinity. So I'm not actually ever going to reach this final term because I'm taking infinite amount of terms, right? So therefore I'm just expressing this part in an expression like this, and I don't need to mention the last term because I'm taking it till infinity, and infinity means that the last term does not even exist because it's never ending. Okay, now that we have this expression, let's write it down. The expected output at time t is equals to lambda summation I from 0 till infinity 1 minus lambda power I y t minus I minus a 1. So we have a nice expression here, and I can call this expression 2, and I can call this expression 1. Remember, when you're doing any kind of steps, try to make it as easy as possible for the examiner. You don't want to frustrate the person who's checking your papers. So what am I going to tell? I'm going to say put expression 2 into expression 1. So expression 2 was as follows, right? Remember, if you have too much clutter, then you won't even be able to think properly because of the clutter. So try to write down mathematics as neat as possible if you want to avoid making mistakes. Okay, t minus I minus 1 plus the error term. So I've substituted in, this was 2, and I've substituted it into 1. Okay, now what do I do? So now that I have an expression here, and let's just write it down. For simplicity, I want I've always done this, that I don't like having too many expressions. So if I have a constant here, I'm just going to take this, I'll just call this constant A, okay, for simplicity, because I want to avoid too many expressions. So I'll write this as A plus beta lambda summation I is equals to 0 till infinity 1 minus lambda power I yt minus I minus a 1. And I'm just going to make a box here so I remember this part. Okay, now listen carefully. What I'm going to do is I'm going to lag this expression by 1 period. Lag, let's call this, we don't have any expression so far like this, let's call it 3. Lag expression 3 by 1 period, okay, and then multiply it by a 1 minus lambda. Okay, what will I get? Let's do it together. Okay, first I'm going to lag this by 1 period, so I'm going to have a yt minus 1, and therefore I'm going to have a it minus 2. I hope nobody's confused about this. And then I said let's multiply the whole thing by a 1 minus lambda. You'll see why we're doing this in a bit. 1 minus lambda, and I get a 1 minus lambda here. I'm trying to speak fast because long lectures are extremely boring. So I want to try to wrap this up. Okay, I'm gonna add we'll get a I plus a 1 here. Where did the error term go? I think we had an error term. Did I forget? Oh, I forgot to write it. Thank God. Remembered it at the nick of time. Okay, there was a ut here, my bad. So therefore, if there's a ut here, there's going to be, if I lag it behind, ut minus 1. Okay, and then I'm going to have a 1 minus lambda into ut minus 1 over here. Okay, so I have two very important expressions. The first expression is this, and the second important expression is this. Okay, I just want everyone to pay attention to first this equation and see that if I open it up, this kind of stuff usually overwhelms most students, so therefore I think this should be done slowly. If I just put in a few terms, let's just put 3 terms, okay? So I start with I is equals to 0. I'll have anything power 0 is equals to 1, right? So I'm going to have a yt minus 1 plus beta lambda. Now I is equals to 1, so this is going to be power 1, yt minus 2 plus, let's just put one more, beta lambda 1 minus lambda power 2 and yt minus a 3, okay? And you can say this continues on till a ut plus a ut. So I hope everybody got this. Let's focus in on this expression right here. And again, let's just get just 3 expressions out. Okay, just 3 expressions. Okay, this is a minus lambda a, and over here we have a b lambda. Let's put in 0. Therefore, I'll have a 1 minus lambda yt minus, if I put a 0 here, I'll be left with t minus 2 plus beta lambda 1 minus alpha lambda power 2 and yt minus 3, and we can say so on. So we have a dot 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 and then our error term. Okay, now the fun part. What I want to do is that I want to subtract this from this. Okay, so let's do it slowly and calmly so that nobody feels overwhelmed. Okay, this is the expression. This was the first, the one in the yellow. So I want to write this first. And I want to subtract this second one from the first. So I want to subtract this expression from the upper expression. And I had a 1 minus lambda into yt minus 1. So I'm looking to subtract. When I'm subtracting, obviously all the positive signs become negative. So this becomes a negative, 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 negative. This positive also becomes a negative. So on the left hand side, I have a yt minus 1 minus lambda into yt minus 1, right? That's easy to see. On the, sorry, this was the left hand side. On the right hand side, we can see a cancels out with an a. And I am left with just a lambda a. So I have a lambda a only. Then I can see actually there's no expression in over here that would remove this expression. So nothing can subtract from here there. So there's a beta lambda yt minus 1 over there as it is. But from now onwards, we can see these expressions till infinity are going to overlap, and therefore this kind of beautifully cancels out. Okay, and therefore we have a 0 0 0 0 0, and then we have a ut in the end minus 1 minus lambda ut minus 1. And then I can write yt is equals to lambda a plus beta lambda yt minus 1 plus 1 minus lambda yt minus 1. So I basically took this over to the right hand side, and then I had a plus any kind of, this is an error term. So for simplicity, I'm taking this whole thing as vt. Okay, now I can take yt minus 1 out as common. So I have a beta lambda plus 1 minus lambda. It's actually nicer if I write it like this. 1 minus b lambda. Oh, actually it's a plus minus lambda. Mostly b and lambda combined should be a fraction less than 1. So it's nicer if I write 1 first. Yt minus 1 plus a vt. As you can see, if I claim that there are no shocks in the economy, then my equation becomes yt equals this expression right here. Right? Does this look familiar? It is a, let's just actually make it even more easy. If I write this as yt minus 1 plus beta lambda minus lambda yt minus 1 is equals to lambda a. For simplicity, let's take this as alpha yt minus 1. Let's just call it g. Now I'm sure it looks familiar. This is a typical first order difference equation where I have taken alpha is equals to 1 plus lambda b minus a 1, right? And the value of g is equals to lambda multiplied by a, where a was equals to small a plus autonomous investment plus autonomous government spending. This is a first order difference equation, and I've already given a lecture that the general solution is equals to the homogeneous plus the particular, and we get basically the initial condition minus the particular solution into alpha power t plus the particular solution. And I also call this y bar, so like you can also call it y bar, which is basically the long run value. Let's calculate what g over 1 minus alpha actually is. G is equals to lambda a plus I bar plus G bar over a 1 minus 1 minus lambda. Oh, it looks kind of confusing. Let's just put it initially like this. And then let's open it up. I'll be left 1 and 1 is going to cancel out. 1 minus 1 is equals to a 0. Then I'll get a minus lambda b minus 1. So lambda cancels out, and I'll be left with a plus I bar plus G bar over a 1 minus a b. Okay, because I multiplied the negative sign in, and I know b is less than 1, so it's even conventionally nicer to write it like this. So we have our solution now. What is our solution? The general solution is yt is equals to y naught minus this. Okay, and then we had an alpha power t plus the particular solution again, which was this. Okay, next, if you've made it till here, congratulations. The difficult part is over, and I want to wrap this lecture up quickly. So let's just talk about the multipliers now. Remember, just memorize this fact that the short run is basically known as the impact period. It is where any kind of shock occurs. So basically it's time t is equals to 0. And in the short run, we basically assume that the value of the previous output is known. So maybe I should write this down. So last period's output, which in this case we can say yt minus 1, is actually predetermined. That is, it's fixed. So thus yt minus 1 is treated like a constant. It's treated like a constant. So when we were looking at our difference equation, which is this, if I take if I write it like this, yt is equals to alpha yt minus 1 plus g, which was lambda a plus I bar plus G bar. I think that is what it was. I wrote G is equals to lambda. Okay, so if this is a constant, then the derivative with respect to G will be equals to 0. So therefore, when I take the derivative of yt with respect to a g to see the fiscal policy multiplier, I'm just going to get a 0 here because that's a constant, and I'm going to get a lambda here because that's the derivative with respect to government spending. So therefore, the short run fiscal multiplier is simply lambda. Okay, now moving on to the long run multiplier. So when we look at the long run, we're basically thinking about time approaching infinity. Okay, what was our difference equation? It was yt is equals to alpha yt minus 1 plus a g. Actually, we wrote it like this. It was there was a minus here and so when I use the lag operator, I put a lag operator here, yt minus 1 is equals to a g, and then I have a 1 minus l yt minus 1 is equals to a g. Oh, sorry, this becomes, if I'm putting the lag operator, it just becomes a yt. Let me make correction here. Okay. And then I have a yt is equals to g over 1 minus alpha L. Remember this, that if g is a constant, then you can't lag a constant behind, right? So for instance, if I had, if I'm lagging a constant, let's suppose 10, you can't you can't lag a 10, right? Because it's just going to remain a 10. So you can't the lag operator here actually does nothing to g, and it actually does nothing to alpha either. So what this is going to be, g over a 1 minus an alpha, which we already calculated as, I think I already did this calculation. What was, yeah, over here, g1 minus g over 1 minus alpha was equals to this expression. So I'm just gonna, I don't want to redo that, I'm just gonna copy it down here. So therefore now I have now we are talking about the long run, so this is the long run. I'm going to take the derivative with respect to g, and it is a 1 over a 1 minus a b. And now we are left with the medium run, and then I'm going to wrap up the lecture. Medium run is basically for time t, not 0, because 0 was short run. So from n naught till infinity is just going to be till time period n. Remember the difference equation was yt is equals to alpha yt minus 1 plus a g. So that means y1 is going to be an alpha y naught plus a g, and that means y2 is going to be alpha y1 plus g, which becomes an alpha square y naught plus alpha g plus g, and then y3 becomes an alpha y2 plus g, and therefore we have a alpha 3 power 3 y naught plus alpha square g plus alpha g plus g. As you can already see a pattern here. So if I have yn, then I should have alpha n y naught plus alpha n minus 1 into a g plus alpha power n minus 2 into a g plus so on till g. Okay, as you can see that leaving the first term aside, I can take g out as common, and then I'll have 1 plus alpha square till I get to an alpha n minus a 1. So I started taking common from here, and I took it till here. Okay, this is a geometric series which is finite. So I can write down the formula. It has n terms, so 1 minus alpha power n over 1 minus alpha, and the value of alpha needs to be less than 1, the absolute value. Okay, we're almost done. Very proud of you till making it till here. The derivative with respect to g, remember this is a constant, and the value of small g was, I've written it down so many times that now I've almost have it to memory. Let's just write this here, and I think g was a lambda a plus I bar plus G bar. So I can take the derivative with respect to G, and it's going to be 1 minus alpha power n over 1 minus alpha and into a lambda. So this is our multiplier, and if you want you can substitute in the value of alpha. So I'm going to be left with 1 minus 1 minus alpha plus lambda b power n, and I'll get a 1 minus alpha plus, why do I keep calling it alpha, it's lambda, and then 1 and 1 cancels out, and then lambda and lambda is going to cancel out, and then we're going to be left with a 1 minus a b. So our multiplier therefore becomes power n over 1 minus a b, and that's it. So that's the multiplier for you. I'll just give a recap. So what we've seen is that adaptive expectations make adjustments gradually, and the economy doesn't jump to equilibrium immediately. It approaches it step by step as expectations basically catch up to reality. So the short run, a medium run, and long run each tell a different part of the adjustment story. So all the multipliers are different. If this helped your understanding, feel free to ask any questions in the comments. I'm always happy to explain further. Thank you for watching, and take care.